Hey, this is Mr. Dow. I'm going to go through the process here of transforming to achieve linearity of exponential data and power data. I'm getting my example from page 768, the Go Fish example, found in the Practice of Statistics, the 4th edition with the flamingos on the front. Before I do anything, I want to look at the graph of this data just to see if I can try to narrow it down. So I have my explanatory x into L1, my response y into L2. I'm going to look at the graph by hitting second y equals or go to my stat plots. And I'm going to make a graph of L1 versus L2. So I've changed my x list to L1, my y list to L2. By hitting zoom 9, I can fit this to my screen. And it appears that I either have exponential growth or a power growth model. I can probably rule out a linear model in this situation since it does appear to be some type of curve. First, I will explore the process of transforming an exponential growth linearly. To do that, I'm going back to my lists. My L1 data, I'm assuming, is already growing linearly. My L2 data is growing exponentially. I need to linearize the data in L2 by taking the log of it. I'm going up to L3, taking the log of L2, press down, and it drops in the linearized data in L3. I now want to find the least squares regression line of L1 versus L3. To do that, it's Stat, over to Calc, Option 4, and the calculator is going to default to L1 and L2, so I have to manually tell it to please go to L1, comma, and L3. Press enter. And I have my least squares regression line on the linearized data found in L1 and L3. I now want to transform this using powers. So taking this information, I'm going to try an exponential model. I'm taking the log of y hat equals 0.069x plus 0.484. Notice I wrote the word log before the y hat because I actually took the log of the y data located in L2 and placed that into L3. I did not manipulate the x data, so I'm not entering the word log in front of it. The transformation takes place by raising 10 to both sides of the equation. And I'm now going to simplify this algebraically. 10 raised to the log cancels out because they are inverse operations. Y hat drops down. And I can rewrite the right-hand side of the equation. I do this by separating the exponents. So I now have y hat equals 10 raised to the 0.069x times 10 raised to the 0.484, which is in the format of an exponential model of y hat equals a times b raised to the x, where my a is 10 raised to the 0.484, and my b raised to the x is 10 to the 0.069x. I can verify that my equation is correct by going through the same process and letting the calculator linearize the data. Here's how I'm going to do that. On the calculator, I'm pressing Stat, going over to Calculate, scrolling to Exponential Regression, option 0 on my calculator, pressing Enter. The calculator is going to default to L1 and L2. I do not want to take the exponential regression of the linearized data. Press Enter. And I have an algebraically equivalent equation. Notice that the correlation coefficient and the coefficient of determination are the same of 0.96 and 0.927 respectively as when I made my exponential model. Keep in mind, the linear regression correlation is measuring the linear relationship. Well, the calculator is doing the same thing when it finds an exponential model. It's giving you the correlation of the linearized data. Let's now go through the process of a power regression. In a power model, we're assuming that the x data located in L1 and the y data located in L2 are both growing exponentially, so I must linearize both of the variables. I'm going to linearize L1 by going to the top of L3, taking the log of L1. I'm going to go over to the top of L4 and linearize the data in L2 by taking the log of L2. I now should have linear growth in both L3 and L4. I would now want to make the least squares regression line of L3 and L4 by pressing Stat, over to Calculate, Option 4. I need to tell the calculator manually to please go to L3 and L4 since it will default to L1 and L2. And I now have a linear model of the linearized data in L3 and L4. I now want to go through the process of taking my linear model and raising 10 to each side of the equation to return this back to a power model. The process is very similar, there's just a few minor algebraic differences. Notice that I have the log of y hat and the log of x because I've taken the log of L1 and the log of L2. In an exponential model, I only had the log of y hat. So 10 raised to both sides of the equation. Once again, 10 and log cancel each other out because they are inverse operations. And I'm going to simplify the right-hand side of the equation. I'm going to separate the exponent, and at the same time I'm going to put 3.049 up to the exponent on top of x. So I now have 10 raised to the log, which is x raised to the 3.049. I have a power to a power scenario. In a similar fashion, 10 and log cancel each other out, and I can reduce. I get my final equation of y hat equals x raised to the 3.049 times 10 raised to the negative 1.899, which puts me in the power model format of a times b raised to the x. Oh, excuse me, I'm sorry. I meant to say a times x raised to the b. I can confirm all this by letting the calculator go through this process, and let me show you how to do that. On my calculator, Stat, over to Calc, scrolling to the Power Regression, Option A on my calculator. It will default to L1 and L2. I do not want to do this with the linearized data. I want to do it straight from the power model. The calculator will do the linear process on its own. Simply hit Enter. And I get an algebraically equivalent equation. Once again, notice the R, the correlation coefficient, and the R square, the coefficient of determination values. They are the same as when I went through the linear transformation. So if I had to choose which model fits best, I want to go the one that has the highest R and R square value, in this case, a power model. Another tip-off for me, since both of these are growth models, power growth models go through the origin 0, 0. Exponential does not. In other words, if the length of a fish is 0, its weight is going to be 0. So if I had to choose which model would fit the best, I would go with the power model, and you can see the transformation that takes place. That process is the same for every problem. And if you have any more problems with this, you can just watch this video over and over until you get it. Thanks.